Hey there, and thank you for tapping into this episode of Bandwidth Coast to Coast. And before you forget, the Earth is trapping more and more heat. Something that I've been noticing over the past few years, which became very apparent to me with the catastrophic where over 1 billion animals died. Something I've been noticing over the past few years, which became very apparent with the catastrophic Australian wildfires, where over 1 billion animals died, is that our narrative around climate change seems to be fixated on only singular grand events. Seeing the sky an eerie shade of orange and the streets of Sydney covered in smoke looks startling and reminiscent of a scene from an apocalyptic movie. We collectively all became shook, and the stories and images flooded all the many channels of media. Corporate news, social media, hell, it even came into our day-to-day life. Then it was followed by massive wildfires in the US, where the same effect of blocking out the sky happened, and even more startling, the east coast of the states were getting poorer air quality and grayer skies from what was happening thousands of miles away. How long did that stay in our collective narrative, though? Fast forward to now, where we've had many more startling events, from a heat dome that killed at least 1 billion marine animals on the west coast, and more wildfires, and the Colorado River officially, and rather late, getting called into drought conditions. Yet, as far as it looks from the hammock I'm watching it all from, that we only tend to keep our narrative fixed on whatever is the most shocking event at the moment. It's important to take time to let the realities breathe. Take in the event that occurred and understand what the trend left unhinged goes. And what are the possible options to push towards better outcomes? Part of that brings in the importance of scientists and people who sift through all the available information and point out what is occurring. One piece of this information came out this summer. Well, my guest, Dr. Loeb, published data he's been working on showing that the Earth is trapping far more heat at a faster rate over the past 2 decades than previously known. This has to do with a whole lot of factors, some as minuscule in thinking, but grand at the margins of time. In this episode, NASA scientist Dr. Loeb spends time explaining the means and mechanisms scientists have to understand climate data, and what he's been working on, and what this means for our planet in the coming century. It's fascinating getting to hear what's going on with our climate systems from those who spend the majority of their days combing over it in ways that far outstrip us average consumers. Well, with no further ado, my interview with Dr. Norman Loeb. Real quick before the episode starts, if you'd like to listen to us on your streaming platform of choice, donate to the show, sign up for our mailing list, visit us at bandwidthpodcast.com. And of course, if you like what you hear, follow, comment, or subscribe to the pod from wherever you're listening. Enjoy! Thank you very much for your time. I appreciate you taking your time to speak with me today about our shifting climatic patterns and what's going on with the Earth today. So Dr. Loeb, if you wouldn't mind, just introduce yourself. I'm going to ask a question as like a baseline question that's unrelated to anything else, and then we'll get going.
Okay, so my name is Norman Loeb. I work at the NASA Langley Research Center. I'm a climate scientist. I lead a satellite project called Clouds in the Earth's Radiant Energy System series, and it is essentially measuring how much of the sun's energy is reflected back to space and how much thermal emission the Earth emits to space.
Okay, yeah, that is all very fascinating. It's like the new rocket science almost. So I ask this question to everyone when they're the first time guest to just kind of get more to our shared humanity. So I want to ask you, what do you like to do that makes you happy?
Well, I like sports. I like playing. There's a sport that I play that I played when I was in my 20s and then stopped and then picked it up again many, many years later. It's a squash. It's a racket sport, and I enjoy that. My body doesn't always work so well with that. I'm getting a little older, so it's been a bit of a problem. Injuries seem to happen more easily than they did when in my 20s. And then during this COVID period, because I'm not traveling, I have more time, off time after work. I picked up another passion that I had in my 20s was to pick up on where I left off 25 or 30 years ago, playing guitar, jazz guitar. So that was my mission to learn jazz guitar, and I think I'll probably keep that one for the rest of my life. There's just so much to learn, so many chords, and it's fascinating. So that's fun. So those are two things anyway that make me happy.
Oh, well, we're gonna get along just fine. Yeah, I've actually been playing jazz guitar for like 20 years. That's
Oh,
like the
really?
yeah, that's the longest thing I've ever done in my life, actually.
Good. Yeah.
Yeah,
Great.
yeah, right on. And yoga, lots and lots of yoga. I'm actually recovering from a shoulder tear from
Oh,
over exercising myself, so
oh,
I know how
yeah.
those injuries nag. So lots of yoga. Someone told me once, "You'll never die," and think, "Oh man, I wish I would have done less yoga." And I've really been
Yeah.
thinking about that a lot. Well, excellent. I'm glad you're able to take some time, especially make the best out of COVID and our shared quarantine, I suppose. Um, so I was perusing the internet, and there's a lot of topics, like most namely the Anthropocene, that I've talked about before in the podcast, and it's kind of a reoccurring research area and topic of talking with guests. So as a part of that, I have all of these like scrapers that are scraping the news and kind of like send me interesting things with some processing of it that pops up. One of them that was like around the middle of June that was going everywhere, which you were quoted in, was talking about that the amount of heat the Earth traps has doubled in 15 years, which seems quite startling. We're kind of been riding the exponent of carbon emissions going up, and I think and you're going to be able to correct me on this, that we have more carbon in our atmosphere than some tens of thousands of years prior. So if you
Yeah.
can just kind of expand a little bit on the heat trapping and what's kind of causing that, and I'm going to kind of have some more follow-up questions from there.
Sure. Yes, you're right. The CO2 level has been increasing. We were about 280 parts per million in the pre-industrial times, and now we're about halfway to doubling the pre-industrial CO2 level. If we continue as we're going, about 2080 is when we'll reach that doubling mark. And so we've seen increase in global temperature of about 1.2 degrees centigrade, which I think is about 2 Fahrenheit. We work in metric mostly, so it's about 2 Fahrenheit. And one of the things that happens when you add these types of greenhouse gases, which are very long lived, is you reduce how much thermal emission goes out to space. And so you don't really change immediately the amount of absorbed solar radiation, but you do change how much heat the Earth sheds to space. So that means you've got more energy coming in than going out. And when you heat a system, temperature increases, which is essentially what we're seeing. But it's not that simple. The initial increase that we experience, there are other factors that change. Like the most obvious is if you increase temperature, snow and ice will melt over the Arctic, Antarctic, and the ice sheets and glaciers. And we're seeing that, especially the glaciers already. Now, they tend to be very reflective. And so that will change that absorbed solar radiation. Since you're melting snow and ice, you're going to reduce how much energy is reflected to space. So you're going to absorb more energy and further cause an increase in temperature. So that's a feedback. So the initial forcing causes an increase in temperature, And then things like snow and ice, there's also water vapor. So when the air is warmer, it can hold more water vapor. And water vapor is also a greenhouse gas. It's a naturally occurring greenhouse gas. It's a very effective and very important one. And so that will, if you add more water vapor, uh, that will increase the greenhouse effect and warm as well. Clouds is another thing that will respond to an increase in temperature, and so you'll have changes in the amount of clouds and the patterns of where clouds are occurring. And since clouds are highly reflective and also impact thermal infrared radiation, that also matters. So that's kind of the knockoff effects of forcing the system. And what we're measuring is the net radiation over time. So we're looking at sort of the cumulative effect of the forcing and the response through feedbacks. And so the record is short. We launched the series instrument in 2000. So we only really have really high quality satellite measurements over 20 years. So again, that's a short period. And the other thing, when you're looking at a decade or two, in addition to the forcing from things like CO2, there's also internal variability in the climate system. We all are familiar with things like El Niños and La Niñas, which tend to occur on the 4 to 7 year period. But there's other oscillations in the system, like the Pacific Decadal oscillation, which is an El Nino-like oscillation, but occurs over longer time scales. So those have to be factored in trying to understand these decade-to-decade changes. And so the result that we found was we looked at 14 years, and we found this doubling of the net radiation that's being absorbed. And I think the other really important part of this study is that we were able to compare with in situ ocean observations. So let me back up a few steps. So the consequence, what happens to the excess energy? So you're adding more energy to the system, you're heating the system. Where does that energy go? Well, about 90% of that excess energy that's being absorbed by the planet goes into the ocean as heat storage, because oceans are very effective at storing heat. The atmosphere doesn't retain heat very well. So only about 2% of that energy is warming the atmosphere, increasing surface temperature. There's another few percent, maybe 3%, that's being used to melt snow and ice, and then the remainder is warming the surface over land. So the 90% then, that's a big number. So there's a lot of energy that's being taken up by the oceans. And when we first started these measurements and started seeing this emerging trend after 20 years, as an observationalist, I'm always worried, is there an artifact? Are the measurements drifting? Is there an issue? Now, we have several satellites with series instruments on, and they were all telling the same story. So that was comforting. But what really put a nail in the coffin here was when we compared with the in situ measurements. So given that 90% of this excess energy is taken up by the ocean, then if you measure the ocean heat content and how that changes over time, that should really correlate well with what we're measuring at the top of the atmosphere. And so my colleagues at NOAA, we've been collaborating over the last 10, 15 years, doing comparisons of year-to-year variations and publishing the results. But this time, I really wanted to see if they were seeing the trend, the doubling of net radiation that we were seeing in the satellite measurements. And so they went ahead, they took these measurements, it's ocean profile measurements. They're autonomous floats. There's about 4,000 autonomous floats throughout the world oceans that take measurements of temperature and salinity as a function of depth in the ocean down to about 2,000 meters. So from that temperature, you can measure the heat content of the ocean, and then the time rate of change of that is directly comparable to what we're seeing in satellite. And so when they got back to me, they were seeing the same thing exactly. I mean, it was astounding how consistent the results were. And so that to me, sealed it for me. This is fairly robust. This is a very robust result. Um, and so we then wanted to know, okay, what's driving it? That's always what's causing this. And so we used other satellite measurements that the Ceres instrument flies with, these imagers that measure in different spectral bands, which you can infer things about aerosols and clouds and surface properties. And so we tried to sort of unscramble what are the impacts of things like clouds, aerosols, melting snow and ice individually on the net radiation. And of course, we have measurements of greenhouse gases like CO2, methane that we can also look at. And what we found was certainly the greenhouse gases played an important role. So part of it is definitely anthropogenic. Changes in surface albedo associated with reductions in particular in sea ice, especially in the Arctic, also had a fairly large impact on the net radiation. And then clouds had a huge impact as well. And the cloud changes are tied to something that also changed during this period. So you may have heard about the so-called global warming hiatus that we had in the 2000s, the first decade of the century. It was in the media all over the place so basically the idea was that global mean surface temperature in the 80s and 90s was increasing fairly rapidly, and then in the 2000s it was still increasing but at a lesser rate. And so climate skeptics were saying, well, where did global warming go? And so it got coined the global warming hiatus. Now, the energy uptake didn't stop. They were just looking at temperature, and temperature, when you think about it, is one point at the interface between the atmosphere and the ocean and the surface being mostly ocean. And so we had a lot of La Nina events in the 2000 period, and when that happens, there's a lot of a lot of the cooler water comes up to the surface, and so that surface temperature of the air would be impacted by that. And so we had this global warming hiatus. The energy uptake didn't really matter because that's the integral of all of the energy. But in 2014, the pattern shifted. So we had kind of a negative phase of the Pacific Decadal Oscillation, which is essentially a pattern of sea surface temperature primarily over the Pacific, where in the warm phase you would have warm sea surface temperatures in the East Pacific, cooler in the West Pacific. And that switched in 2014. And the sea surface temperature patterns were warm over the Eastern Pacific, where you have a lot of marine stratus clouds, which are highly reflective. And so that is part of the story here, because we saw this huge cloud pattern change associated with the warming of the Eastern Pacific SSTs. So it's a bit of a complicated mess. It's a bit of, you have anthropogenic forcing that's certainly playing an important role, but then you have internal variability that's also playing a role, and they're kind of coming in phase to cause a perfect storm to generate this doubling of the net imbalance. And so that, in a very long-winded way, is sort of what's causing this. Now, from the observations alone, I can't say what percentage is anthropogenic and what's internal variability, because as I mentioned, it combines everything. To do that, you need to do a lot of model simulations using sophisticated climate models, which I'm starting to do with modelers now. So the work that we published has raised a lot of questions that we want answers to as best we can.
I'm excited to keep following your work. So I, as a point of just kind of my own personal study and way of thinking of the world, is that I like to spot emergent qualities and emergent trends and try to like build the smallest function that then extrapolates into whatever. And part of that, I think, the concept of a virtuous cycle is one to kind of use. And in this case, it's if I'm transforming what you're saying into like trying to make it the most atomic way possible, is that all of these combined forces of energetic, emissions, all of these different changing of the air chemistry of the Earth, and all of it is creating a virtuous cycle, which is then fueling itself to maintain itself going forward and changing the ocean temperature, which then has an effect on all of the other cascading systems, which then continues to perpetuate and continue it. Is that a way of putting it?
Well, the way I look at it is, if you've seen a good example is you look at the global mean surface temperature record. I don't know if you're familiar with that, because it goes back to 1850. We've been taking measurements of surface temperature for a very long time. It's only recently that we've really been taking quality measurements of things like the net radiation, which is in the paper. So if you look at the global mean surface temperature since 1850, what you're going to find is a long-term trend that's very obvious, but superimposed on that long-term trend are a lot of fluctuations. And so the long-term trend is primarily driven by anthropogenic forcing of the climate system, increasing greenhouse gases. The fluctuations, which tend to be shorter timescales, are more those cycles that you're talking about, that internal variations in the atmosphere and the ocean that cause a lot of noise. And that's why I say, looking at 15 or 20 years, it's a bit more complicated because you've got the forcing, but you've also got this internal variability. Now, if we had 60 years of net radiation measurements, we probably would be seeing something much more like the surface temperature record.
So it's like a sine wave. It's going up and down, and there's some
No,
variability.
actually, the long-term trend is clear. It's not. It's just sort of a long-term trend, and then there's a lot of
That's what I meant by that. Yeah, the variabilities.
Yeah, much shorter frequency variability superimposed. And so the global warming, so-called global warming hiatus, is an example of that. Nobody was surprised really that happened, because that's kind of what the system does, is it fluctuates. But what you really want to look at is the long-term record and the long-term trends. And so my hope is our 15-year of doubling of the Earth's energy imbalance, I'm hoping for all of us that this is a big part of that is internal variability, and it shifts. I mean, we're not going to get rid of the anthropogenic part, and that's there. That's going to continue. But yeah, because it has consequences. If you're heating the system, it does matter because there's symptoms that come with it. Global mean surface temperature is one. You're going to melt, if you're adding more heat to the system, you're going to melt snow and ice. So that's going to cause sea level rise. The oceans are fluid. So if you heat them, that also causes sea level rise. And where I am, that's a big deal. I'm right on the coast, right? What other extreme weather? If you heat the system, yeah, you're going to see more. There's more energy. And so you're going to see more severe weather, droughts, floods that we're seeing right now and out west. And so I'm hoping that the next 15 years, the part of this that's internal variability kind of mitigates to some extent the part that's anthropogenic. And we won't see all of these terrible things I'm talking about. I mean, we will to a certain extent. It's just a matter of what degree.
Yeah, which order of magnitude. How much is the ocean? How much does the ocean play? So the ocean is like what, 76% of our surface?
About 72, 71, 72%.
Okay, so it's 70-ish% of our surface. How much is it responsible for our global weather patterns?
Well, there's a lot of interaction between the atmosphere and the ocean. It's a coupled system. So you can't say what percentage is the ocean and what percentage is the atmosphere, because there's a lot of exchange of energy between the hydrological cycle is essentially energy that's evaporated from the ocean that goes into the atmosphere, and then you have precipitation. And so there's this cycle that of interaction between those two. And what fuels that is energy too, right? The energy that's absorbed from the sun at the surface is used for evaporation. So that kind of sets the sort of it sets the match in a sense for the system to work. So you can't say what part is ocean and what part is atmosphere. They're coupled.
Yeah, well, I guess that even answers the question in its own right, though, because you can't look at. I mean, I think most of us, because we're terrestrial beings, right? Think of the Earth and like the physical land we're on as the reason for the rain, or and there is like some variability in that. Like I just moved from San Diego. That's a great example of a microclimate, and as you move east towards the mountains, how the mountains play into the different ecotones. But in reality, all of that is largely affected by the atmosphere and the ocean, which we've most recently seen with the heat wave in the Pacific Northwest, right? Because that was mostly caused from an oceanic heat dome effect,
right?
Right. If this trend continues, and this heating continues and this energy continues and the trapping of more, how much? Well, I don't know the degree you're going to be able to answer this, but will our climate fundamentally look different? Like, will the climate of certain areas, like the Pacific Northwest, fundamentally look different than it does now? And is that going to be an effect that is felt largely across the whole of the marble? Or do we not even know?
Well, to say how one region is going to look does depend on a number of factors, and I can't say what Oregon is going to look like or Washington's going to look like.
But are they going to be affected by it? That's more what I mean by that.
Yeah, certainly. I think the easiest way to think about these, because climate is really kind of statistics of weather, right? And so you've got a distribution of events that happen. And so what you're doing when you're forcing the system and heating the system, you're shifting the distribution. And what you really want, like extreme weather, is really the tails of the distribution. They don't happen frequently, but when they do, they cause a lot of damage, a lot of destruction. And so you could imagine if you have a distribution with a tail, and you start to shift the mode of that distribution, well, you're going to see more of the extreme weather that occurs at the tails. And that's going to be true of many places. So potentially more droughts and more floods, those parts of the world that see that kind of weather. You can see hurricanes being more intense. You'll see more Cat 5s because, again, there's just more energy that's fueling these events. You'll also see shifts in patterns of the weather because the general circulation is going to respond as well to having more heat in the system. And so you could have places that were more arid become more rainy all of a sudden. Part of the regional prediction is tricky. So here again, we have to rely on climate models to tell us locally what's likely to happen. From the observations, which is really where I live, is observations world. We can't really say, how things will change. We have to turn to climate models.
Yeah, that makes sense. Is the rate of change that we're experiencing out of the norm of what we've known historically, or I mean, I guess history is a terrible term, geologically? Like, is the pace in which this change happening?
Yeah, certainly the last 100 years are unprecedented in terms of the amount of change. So prior to having anthropogenic forcing, changes in climate were much more gradual and were, time scales more of tens of thousands of years associated with how the Earth moves around the sun, the orbit. Um, but there's no period that we know about where we had so much change in like 150-year period. That's definitely, so the acceleration is there. And the other thing were the early results we're finding from the work we're doing with the models that follow this study, and it's very preliminary, so I probably even shouldn't mention it, but I will. But the sense I'm getting is if you run climate models for like many what they call ensemble members, you initialize them in different ways, and you run thousands of simulations and over hundreds of years with forcing. You then ask the question, statistically, is the 14-year period that we studied in this paper, where does it lie when you look at the distribution of many, many simulations? And the interesting result we're finding, again, preliminary, is that the models tend to underestimate what we're finding. So very rarely do we find 20-year periods, say, or 14-year periods in the model simulations with a trend in the net radiation or Earth's energy imbalance is as large as what we observed. And so it's an interesting result. And we haven't dug into why that is, but that's sort of what we're finding so far. But again, it's preliminary. But that's the kind of thing you want to do, is you want to take these observations, and if you have a surprising result that's robust from observation, then you ask the question, do the models, does the modeling world replicate what we're observing? And if not, why? What is it about the model that isn't working right, for example? And that's how we learn. We learn from seeing differences, and then there's a community that does model development, and they improve the models, and then we make sort of slowly steps forward.
I'm going to ask you to take a sidestep question. And could you explain what a climate model is?
So a climate model, I mean, people are familiar with weather models, right? People, our forecasts are generated by these numerical models, which are a bunch of equations, a bunch of complicated equations that represent the physics of the atmosphere, the oceans, land, and the cryosphere. So all of the fluids, the flows of fluids are represented in these models. And so that's what essentially we rely on for our weather forecasts. The models that are climate models are similar to that, but they're a little bit different in some ways. Now they have to worry more about the longer term, which ironically is a little bit easier to predict, to project forward than weather. Weather is very difficult over, let's say, 2 weeks. It's a very difficult thing to do, but when you average enough time, things actually ironically get simpler. And so the models are going to have to be fed the forcing scenario, the projections of how much CO2 is going to be in the atmosphere, how much other gases are in there. And so they represent the physics of the atmosphere, the physics, like I mentioned, all of the physics that are taking place. And they're not necessarily meant to predict this decade. They're meant to predict, sort of project forward. So if you said, if we continue as business as usual in terms of how much CO2 we're emitting into the atmosphere, the models are going to project where we're going to be when we double CO2. And so there's many of these models all over the world. The US certainly has a few, Europe, Japan, China, they're all over. And so these different models are all running projections of forcing from things like CO2, and then they're all comparing against one another to see how consistent they are for a given scenario, forcing scenario. And so what we're finding is that So I mentioned we've warmed already 1.2 degrees Celsius. We're about halfway in terms of doubling CO2. And once we do double CO2, which is really one of the experiments they run, is what is the mean temperature of the Earth, or what is the increase in temperature of the Earth at the doubling of CO2? And they're projecting about 3 degrees Celsius from where we are, 1.2. But there is some spread about that. The 95% confidence is about 2 to 4.5 degrees, which is a large range. When you consider the last ice age, the temperature was in the other direction, 5 degrees cooler. So here we're talking up to 4.5 degrees warmer, which is a big number, and hopefully we won't see that. And so part of our job is to reduce that uncertainty. And that's one of the other things our observations are being used for. So I mentioned clouds earlier. They are one of the big reasons why there's such a big spread, 2.5 to 4.5 degree, or 2 to 4.5 degree spread in what's called climate sensitivity, which is the temperature of doubling CO2. Clouds are very difficult. They're very important in terms of the energy budget of the planet, but they're very difficult because you have to resolve scales that range from microns to, thousands of kilometers. And so that's where we struggle. That's where we really have to do a lot of work to narrow the uncertainty. And so it's an interplay between observations, being able to use the observations in clever ways, make field campaigns where you can measure at fine scale, and then compare the models against each other. And so we've been making progress, but it's pretty hard. It's
Yeah.
But 3 degrees is about where we think we're going to be when we double CO2, likely around 2080. That's our best sort of, the consensus sort of result that we're thinking.
Which Leonardo DiCaprio, like shortly before we were recording this, made an Instagram post that went viral that was talking about 1.5, 2 degrees and 3.5 degrees, what that would actually mean. It's quite startling, mostly because of the unknown unknowns of what that would mean. How much of our current climatic understanding of the way our air chemistry is changing in regards to carbon and other greenhouse gas emissions takes into account the anthropogenic causes, so the human causes of this from all of our emissions, and how much is also because of the cycle that creates for things such as the permafrost and that melting and releasing more carbon and other locked gases.
Well, that's part of it. That's all included in these simulations, as well as the feedbacks that take place, right? That's, again, without the feedbacks, the warming wouldn't be as dramatic. If it was just sort of increasing greenhouse gases, we would see a few degrees warming. It's really these feedbacks that are exacerbating the warming. It's the changes, the response of the system. So it's what we call positive feedbacks. I mentioned a few: the snow and ice, the water vapor, and clouds in particular. So the permafrost is certainly part of that forcing and response as well. So because you increase temperature, you melt more, you emit more, and the cycle continues. Or the feedback cycle continues.
Yeah, I was talking to Dr. Heiko Balzer. He's at the University of Leicester. He does a lot of satellite work and satellite imagery work, mostly on forests and what's happening there. And I mentioned this to him, but the permafrost melting is something that has kept me up at night sometimes once I learned about that a few years ago, because of exactly what you're saying of the feedback cycle that brings, and just the unlocking of more carbon, and then the kind of existential conundrum that brings. So the past 150 years versus now, there's definitely been an increase. Is the pace of the increase projecting going forward increasing as well? Because something I think about a lot in both socially with our use of technology, as well as the way we're kind of approaching the real Anthropocene here, is kind of riding the exponent. Like things in my eyes, the chaos in the system of just reality seems to be going up vertically. Is that also the case in this, or is the emission and pace of all of this starting to increase at a faster pace in this coming decade versus the past 30 years?
Well, I think again, I'm hesitant to talk about one decade because again, it's a short time scale on in a climate sense. And again, a big part of that is because the oceans operate on much slower time scales than the atmosphere.
Hmm.
So that I wouldn't want to say one decade. Like the 2000s, we saw a lot of La Niñas, which made things cooler a little bit or less. The increase in temperature was reduced. It wasn't cooling. It was just that the rate of warming had been a little bit less. So I wouldn't want to talk about one decade. I think you want to talk more about 30 to 50 years, where you start to get above that just cycles of internal variability. And so, yeah, we are seeing an acceleration in changes in the system. And of course, we're concerned about tipping points where there's the feedbacks I talked about kind of take over and there's no return. That's scary and that's unknown. I mean, there's a lot of uncertainty there as well as when do you reach a tipping point. So again, these are open questions at this point, but they're certainly valid questions.
You don't have to answer this, and you can totally say that you're not comfortable. But could we possibly have already reached the tipping point that we don't know about?
I don't think we have. I think we still have time, and people who study this a lot more than I do are talking about 10, 20 years for various reasons, and there's a lot of debate amongst climate scientists about those types of questions. So personally, I don't think we have, and I wouldn't want to say it's going to be 20 or 30 years. I think it's a very difficult question to answer. And again, we have to rely on models. You can't just extrapolate observations and say, there you go, there's the answer, because it doesn't make, to me, that doesn't make sense. It's not that simple.
Okay, I like that little bit of hope. I'll hold on to that. And the part that you mentioned earlier that was really fascinating to me, and also kind of speaks to the complexity and the degree of difficulty and even understanding this as a reality, right? Like there's the theory of more carbon in the atmosphere, it's going to mean heating. But then when you start breaking it down to all the component factors of that, like you were explaining, and even struggling to do so because it's so complicated and it's so interdependent and interconnected, is how much of our heat and energy reduction is shed into space. Like that is something that I never would have really considered before, that a lot of our Earth system is actually floating in space, and actually that the radiation leaving the Earth versus being trapped there, kind of also, in my eyes, I'm kind of going to be unpacking that afterwards, is how much the layman doesn't understand, or it doesn't even know to understand, kind of that unknown of the complexities of this incredibly large system.
Right, but anything that has a temperature emits heat, right? It's just sort of a basic physical law. We're emitting heat all the time, which makes why infrared cameras can see us, and so the planet's no different. And that balance, that energy balance, I think there's a lot of complexity, but there's also a beautiful simplicity to it. It's simply energy in and energy out, right? If you heat the system, the sun is our fuel that drives the climate system. And so we absorb solar radiation. but we shed heat. The planet sheds heat by emitting thermal infrared radiation. And if those two are equal, then temperature when averaged over a long period won't change. If there's more energy going out than coming in, then temperature is going to drop, or vice versa, temperature will increase. So that's kind of the simple explanation. But yeah, under the hood, there's a lot more complexity when you start to look at these feedbacks in particular. And as I mentioned, those are really important for actually trying to project how much warming we're going to see. And the one factor out of these feedbacks that's the most complicated so far is really the clouds. We really are struggling with what is the response to doubling CO2 from clouds. And the consensus is that the cloud distribution, there'll be less low clouds, and those have a big impact. So the cloud cover, the low cloud coverage over the planet will decrease, which will mean that essentially more energy is going to be absorbed, because that low clouds, their temperature is similar to what the temperature is at the surface. And so in terms of thermal emission, they don't have much of a radiative effect, but they're bright, and so they reflect a lot of energy. And so if you start to reduce how much low cloud there is, well, you're going to absorb more energy. And that's what the models are showing, but the models are showing fairly large discrepancies in the low cloud feedback, which is really one of the reasons why there's this spread in 2 to 4.5 degrees warming after doubling CO2. So that's kind of the holy grail in climate research right now, is understanding the cloud response to warming.
That's fascinating. I've never even heard that anywhere. And I mean, I'm a layman, but I spend some nights and weekends looking at this quite intensively, and I've never come across that. That's quite fascinating.
Well, the other big uncertainty I mean, these are problems that we're struggling with in the research world that matter. They're all things that affect our ability to project what a given forcing scenario. The other one that we're studying hard is the role of aerosols. So these aerosols are tiny particles suspended in the atmosphere. So dust is an aerosol. Pollution, those are aerosols. Sea salt, when you have wind over the water, it generates salt particles that are suspended in the air. So those particles, a cloud can't form without an aerosol, right? The water condenses on a particle and it forms a droplet. And so changes in the abundance of aerosols will impact the clouds as well. And so it's something called aerosol cloud interactions. That's another hot area of research, is to understand, because one of the things that's happening is we are getting better at cleaning up our atmosphere, off the US, off of China, over Europe in particular. Things are cleaning up, things are getting better. We're switching to cleaner sources of energy. China in particular, I mean, it's really bad there, but they're putting some pretty strict measures, control measures, to clean the air up. And so that means you're going to change how many aerosols are in the atmosphere, and you're going to change types of aerosols that are there. So then you want to know, okay, what is the impact of that on things like clouds? And so that's another big area that people are studying.
Wow. There's this Socrates quote that I love a lot. I think about it a lot. And it's someone asks him what wisdom is, and he says, "All I know is I know nothing." And that makes me think of what you're saying right now, is just how complicated all these things are. Like, you fix one thing and it might have unintended consequences, and something like an unknown you didn't know to consider, and what the resulting effects of that would be.
Yeah.
Yeah, that's interesting. Is there anything other than the doubling that you've most recently published that has been quite startling with you when you're looking at this research?
Well, a paper that I wrote that preceded this looked at this switch in the Pacific Decadal Oscillation and looked at climate models, how they whether or not they replicate the change. So after 2014, when the PDO, the Pacific Decadal Oscillation Index, changed sign from cold phase to warm phase, we had, as I mentioned, a lot of warming over the eastern Pacific, which is where the marine stratocumulus clouds, like you're in California and you're familiar
Marine
with those
layer,
low
yeah.
clouds.
Yeah.
Yeah, it's a marine layer. When you fly into places like San Francisco, you see this beautiful layer of clouds. But those are fairly extensive and, again, fairly important to our energy budget. Um, and so the change in surface temperature, sea surface temperature, associated with the flip in sign of this Pacific Decadal Oscillation caused in the observations this huge reduction in low cloud and this huge uptake of energy locally. And when I first saw that, I thought, oh my gosh, this is, I mean, it was pretty unprecedented. People were calling it the marine heat wave. You know, it was because it was contributing to warming in California because you reduced how much cloud there was, and it was just all this extra energy that's being absorbed and had an impact. And so I wanted to talk to some climate modelers and see if they were able to replicate that response to that change in sea surface temperature. And unfortunately, so probably every 7 years or so, the climate community releases a report called the IPCC, the Intergovernmental Panel on Climate Change. I don't know if you're familiar with that.
Yeah,
IPCC reports.
I read one of those a few years ago. That is the reason I stay up at night with the permafrost.
Yeah, those are great documents. I mean, there's just thousands and thousands of scientists across the spectrum work on these. So they're really, it's just an incredible effort and an incredible resource. Well, the modelers end up doing a lot of simulations to support the analysis that goes in. And unfortunately, the model runs ended in 2014, right when the PDO switched sign and all of these changes were happening. And so I couldn't just grab model results to compare with my observations. And so I was at a conference in Germany, and I was surrounded by a number of these different modelers from the US, from different parts of Europe. And so I went around with my laptop terrorizing them with images of what we were seeing in the observations, and said, do you think your model reproduces this? And they were like, oh, I don't know. That's a good question. Now, the problem is they had to work. They had to run their models for another 3 or 4 years in order to answer the question. So I was able to twist about 7 groups to do that. 7 of the best climate models in the world. It took a couple of years because everyone's busy. And so, yeah, I was able to compare. And what they did is they were given the sea surface temperature, and they were running an atmosphere-only model. And the question was whether the cloud response was consistent with the observations. And the surprising result there was that by and large, they were doing the right thing. By and large, the models were getting it right. The magnitudes were somewhat different in some cases. One of the models was way off. I mean, it was looking at a different planet altogether. It was just totally out to lunch, which was a surprise. And the group that represented that model weren't very happy about those results. But the US models did very well and replicated the results. So that gave everybody hope that, you know, the models aren't completely out to lunch. There are things in there that they're doing right. And there are things that, you know, still need work. So that was, I think, a fun paper to write, because it was finally saying something positive about, you know, the model world.
Yeah, yeah. That's gotta be feel very nice. It's like a little bit of satisfaction and delight, I bet. It's just like an anecdotal point. Like I used to live in San Diego, and I in the places I lived while I was out there for several years, I lived in, just if anyone is listening knows it, is North Park, which is like just north of Balboa Park. It's like on top of quite elevated place. And then from there, I went 7 miles away, and I was living on the coast in Pacific Beach. And in North Park, we never got any marine layer. It was never, we never got any of the low level clouds in the morning. So like, from, I mean, mere minutes after the sun rose, it would be blazing hot, and there'd be no reprieve, no clouds, no nothing. And then when I moved just down the road to Pacific Beach and along the coast, every morning was chilly, like very chilly.
Yeah.
And then there was, like an hour, sometimes an hour, hour and a half of when this marine layer is getting burned off from the sun rising. And it was startling to me, like how different the two different climates in that microclimate are. But if you're extrapolating that across an entire coastline or across a much larger area, I could definitely see how that could contribute to, kind of an effect on the whole system. And um, it once again kind of goes into play of just how much there is to consider in this upcoming. I don't even know how to put a timetable on it, but just the upcoming events that'll be happening over the next course of time. Um, it's it's always interesting how much how much is happening in regards to all of this, and how much is really shifting. Um, yeah, well, thank you for your research and your work. I mean, this is really fascinating. I hope more people are, starting to kind of getting their eyes on this type of stuff and understanding really what this all kind of means and contends with. Because if we like it or not, this is definitely what's going to be affecting us for the rest of our lives, regardless of where we are. And I think it's only going to bring more conundrums in the future.
Yeah. Well, I certainly hope that things do turn around and the doomsday scenarios don't come to pass. And
Yeah, well, I think we'll see. I have, as like a point of philosophy, I try not to generate hope because it's like a passive act. I try to build faith, and knowing that there are more people out there that are working on things like this and getting the word out. I mean, I know that it was, a very startling research that you did, and I know that that's part of the reason that it got, spread as far as it did. But I did see it everywhere, and even just, preparing for this interview again, searching your name came up with how many different periodicals, use that. So I think it's good that people are starting to get this understanding. The thing that I worry about, and this is just anecdotal, is just how much noise there is in our daily lives and how much there is to consume as far as like from a media and just like state of being. I mean, we have so many different bills coming due at the same time. And then we have all these advances in technology and viruses and everything that's all just kind of coming to a head at the same time. Like that is my biggest concern. I mean, I think that humans have always been quite great at adapting and overcoming circumstances, but we need to have a shared understanding of what the problem is.
yeah, and I mean, what to me the importance of that study is not just the result. Um, I think from an observationalist point of view is the robustness of the result. That
Mm-hmm.
two very independent ways of measuring gave the exact same result, and that to me is important because if our observing system is telling us different stories depending on what approach we use, what instrument we use, that just causes a lot of confusion, a lot of noise, and a lot of wiggle room for pretending there's no issue. Um, so that's an important part. I think having a sound, robust observing system where it's, there's no question that this is happening. It puts the onus on us to really look at this as something real. So that was for me the biggest sort of, the fact that it doubled was alarming. And I think again, I'm hoping that a big part of that was internal variability, and it can turn around in the next 15 years. What keeps me up at night is that we're, you know, is making sure we maintain these observations over multiple decades so that we can have a better sense of what's actually going on. And it's not always a given. These programs are expensive. These instruments are expensive, and so I hope that we continue these. I'm certainly trying to make sure that we do and do everything I can. But it's not like just measuring temperature at the surface, which you can do fairly cheaply and fairly accurately. But launching satellites and doing this in a way that doesn't keep changing. You can't change the ruler midstream, because then you won't be able to measure. You won't be able to unscramble whether you're looking at changes in the climate system or because you changed instrumentations. So there's a lot of details that need to be considered to properly observe the climate system, because we are looking at subtle changes over time. So those are the things that keep me up at night, that are related to my job. Of course, things like what you mentioned keep you up at night also keep me up at night. So it's a wonder I sleep at all.
Well, hopefully all the squash has some part to do
Yeah,
with it.
yeah.
Well, I'm glad that you made that point, because I hope that more people start getting active. I try to look at everything as neither good nor bad, and I think if I'm looking at COVID and kind of the last 18 months of what that has looked like, I think one of the things is that we have more people that are fixed in their echo chambers, but we also have more people that are now observing more and questioning more and wanting to know more and getting more engaged. So I hope as a proxy of that, things like this do get more research, because kind of like, back to my unknown unknowns, is that if we don't even know and we're not measuring and we're not, actively trying to understand more, then there's going to be more that's going to blindside us.
Right.
And in something as large as this and complex as this, and how much something like a changing climate would affect us, I think it's quite important. Like there was just an article I was reading yesterday about the changing in our forests and how much drought in the West and different shifting heat and things like that are leading to more problems, like species like trees and things like that. Like they don't change as quickly as the Earth is changing, and what that's all going to lead to. But the more that we understand it, and the more that we kind of have that shared measurement and understanding, you can't make any action without understanding what you're trying to solve for and understanding what you're dealing with.
Yeah, and that's so another point you didn't raise that comes up every once in a while, is this whole idea of geoengineering. I don't know how familiar you are with that. That there are people that are taking that very seriously, and yeah, that the scientific community, the bulk of the scientific community, when they are faced with these engineering solutions, it's exactly what you're saying. It's the unknown unknowns. What are the unintended consequences of doing some of these things that can cause more harm than good? And even their effectiveness is in question. So it could be that they're not effective at all, and they're causing other unintended consequences. But there are people that are very serious about this geoengineering thing. It's scary.
It is scary, and I try my best to not dismiss anything wholeheartedly. But whenever I come across like some ideas in that realm, I'm always just like, God, I feel like there's so much more that we're not considering. Like I don't know how frequently they do it, but I know in Dubai, I believe it's sodium nitrate or not sodium, silver nitrate that they inject into the atmosphere to cloud seed to create it to rain, and doing things like that. Like it's very futuristic, and I think us as a species have a hardwiring for novelty. So I think it's very cool, and that definitely sometimes I think can emotionally lead us astray. So I think it's really cool if I'm thinking from it, just like kind of a base novelty and delightful reaction. But in my mind, that seems awfully scary in what we're actually could possibly be doing, especially if we start doing that at scale. To exactly what you're saying, I think that we really need to be understanding more, because I mean, like, there was some understanding. Like, there's a news article or news like clip that I came across when I was doing some research of, it was in the late 1800s or early 1900s, that was postulating the idea of putting more carbon in the atmosphere could potentially raise the global atmospheric temperature. And I wonder if how many of those things that we're not thinking about, right? Like, I worry more about what we're not thinking about when we do things than what we are thinking about or what our intent is.
Right. Yeah.
Yeah. Like, the road to perdition is paved with good intentions, right? That's something I think about a lot.
Mm-hmm. Mm-hmm.
All right. Well, this was very fascinating and stimulating. I really appreciate your time, and I'm going to be looking a lot at clouds after we get off the phone. Is there anything else that you want to mention while I still had you?
No, I think we covered it well. Good job.
Thank you very much. I appreciate that.